That's right, you haven't gotten rid of me. Today we're talking about functional resonance analysis, fancy term for something that's actually not that complicated, and about diagramming your system. So if you thought you were done with diagrams and graphs after the last talk, no. Just as before, we've got a QR code up there that's got a handout that links to essays about this sort of stuff, how-to guides, free software, books, and my contact information. But my goal for today, and I have 20 minutes to accomplish it, so we'll see if we can pull it off, is for you to be able to interpret this graph. I want you to be able to read it. I want you to be able to reason about it. I want you to be able to intuit a little bit of the dynamics of the system it represents. I want you to have the foundational tools to start making graphs like these for your own systems. And if possible, that will therefore give you enough to go on to decide whether or not it's worth doing for your teams and your systems or not. I'm presenting a tool here and trying to teach you a new skill within 20 minutes. That's the exchange. 20 minutes of time from you. I give you a new tool. Maybe it's helpful for you, maybe it's not, but it only costs you 20 minutes, so it's not that big a deal. And it's called the Functional Resonance Analysis Method. We call it FRAM. It was put together by Dr. Eric Hallnagel, one of the leading figures in what's called the resilience engineering movement, which has popped up in various talks and tracks and SREcons for probably going on 5 years now. But it's cool stuff. But the question is why? What's the point of this? How will it help? And fundamentally it comes to, is it good to think with? This is an attempt to diagram your system, and in the act of diagramming your system, understand it a little better, understand its actual dynamics, how it works and how it behaves. And so, whether or not you use this and the way you approach it should entirely be driven by, what am I trying to get out of this? What part of my system am I curious about? What do I want to understand better? And so the barriers to that generally are relative ignorance, and I don't mean that in a negative context, but you know the parts of the system that you work in. Maybe you don't know what your teammate's up to, or maybe you do, but you don't know what your partner team is up to, or maybe there's an upstream dependency you don't understand super well, or maybe there's someone who's dependent upon you who you're not quite sure how they're using your output. Various vendor technologies, so on and so forth. There's always something somewhere, and so there's relative ignorance. There's also complexity, which means when things interact with things, you might be able to intuit a relationship, but when things interact with things, it gets a lot more tricky to follow. And intractability, which comes from that, the difficulty in imagining and walking through a scenario. So, what are the principles of this method? It is a method first, and the model is secondary. So one of the cool things about it is that you get a model out of it. You get a little physical artifact that says, look, I did some work. Because this is work. It's cognitive work. But cognitive work, thinking about your systems, is still work. It just doesn't show up in your story points. But the value in this is in the act of creating the model, not in the model itself. But the first principle is that we care about functions more so than components. Functions are the core and central element of this modeling approach. Right? It's not the node, it's not the controller, it's not the cluster, it's the behavior. It's a behavioralistic approach because in the end, when you want to figure out the performance of your system, it's what does the system do? Is it inherently superior than doing components? No. But it's different, and in being different, it forces you to think about your system differently and understand it better. The next thing is that failure is equivalent with success in this model. It's not, oh, the system failed to do X, Y, and Z. All it cares, how it defines things is that there's variability in the output of functions. It might be slower or faster. It might give a high value or a low value. This is abstract now. I'll give some concrete examples in a minute. But as far as the system is concerned, there's no such thing as failure. There's just, it gives you this output. How does that affect things downstream? Another principle is that of emergence, which I talk about all the time. Right? The idea that Behaviors can come out of connections in multiple pieces that you wouldn't see in the individuals. And a classic example is cellular automata, which you may have learned about in school or played with somewhere, where you've got a grid and you've got rules about what color things become at each clock tick based on the color of things around them. And that can result in all sorts of interesting things that look lifelike and that move around and look like they shoot things and things like that. The left is an example of a classic cellular automata. The right is an example of how would you describe it? A more fluid one, right? They've continued to develop these, and so that's still cellular automata, but it's in a more advanced, cool way. And I just linked it because I think it's cool. But it gives the idea. These behaviors that come out of very simple rules, but give you very complex behaviors you wouldn't have seen before. Your systems do the same thing. They can surprise you in what they do. The other principle is resonance, which is in the name of the method, right? There's stochastic resonance and there's functional resonance. When we talk about functional resonance, we mean the variability in a function and how it affects the variability of functions attached to it. In the diagram here, we've got examples of constructive interference and destructive interference, right? Dusting off the cobwebs from your physics education. When you've got two wavelengths, and if they hit each other and their peaks coincide, then they can make an extra big wave. Or if you have the reverse, then they can destroy each other's peaks and flatten out. That can happen with variability in your system as well. You can have something that's very variable feeding into something else that's very variable, and so it gets really out of control and causes an incident. Or you have things that are really good at dampening the effect of troublesome things upstream. So, looking at the models themselves, once again, I want you to be able to interpret what this is. And in this particular example, I went out of my way to model one that is an incident response system, right? So it's more people and more thinking and less the software and technology. But I have another example of that you'll see a little bit later. But the point is that this is for the general systems, which include the people and include the organization itself. How do we figure it out? Well, we start with hexagons. Core unit. Each function is a hexagon. And each function must have an input, right? So the input is what kicks off the function. Makes sense, right? It's kind of in an abstract sense. If you've got an open the door thing, the input is a door that is closed. Output, every function must have an output. If your function is lock the door, the output of the function is a door that is now locked, when previously it was not. That's all relatively straightforward, and those are the hard requirements, is you must have an input or an output unless the function is on the edge of your system. And this will start making more sense in a minute. But what's the next piece? Resources. These are consumable things necessary for your function to be carried out. For the function drive to the job site, it would be gas. For the function save the file, it's storage capacity. These are things necessary for the function that can be exhausted. Not every function has them, but many do. Preconditions. These are similar to resources, but they're not exhaustible in the same way, right? So in a medical example, and a lot of this was innovated in the medical field looking at surgical processes, is if the function is close up the wound, then a precondition for that is check that you've accounted for all the surgical tools so that you don't leave one inside them. That's a thing that has happened. It's a case study in FRAM, in fact, and apply the analgesic so it doesn't really cause other problems. Time, right? There can be temporal components that are not directly tied in the way that preconditions are. If you've got a ship that needs to go somewhere, its function may be dictated to some extent by the ship's sailing schedule. Like, it may not be that some previous function says, we gotta go now, but the schedule says, we need to depart now. And so the function ought to be kicking off. And lastly, there's control, which is how the function does what it does. In the case of anything incident response related, it might be dictated by your runbook. Or the sailing example, it might be dictated by the ship's standing orders. Policies, code deployment configuration. This is largely set by at an organizational level, especially for the kinds of things we deal with. And what do you do after that? You just start connecting them together. Outputs from one function become inputs for another function. Right? You've got a function that's verify system health, and the output was there's a fault. That becomes an input to another function, which is, well, let's create an initial mitigation plan. Right? This is a cognitive example. Simple at this point, then it starts to get more complicated. This is a more software-driven system where you start tying them all together. This one, without getting into all the details, and this is not an Indeed system, to be clear. It is a real system, but it's not one of my employer systems. You've got to spin something up in Kubernetes, and it's got to go check whether or not there's a diff, and then it's got to get the files from that diff on that storage device, and it needs to upload them to the cloud. Right? And this is a small corner of that. When things start to look like this, where you've got all of these connections. So I'll let you look at that for just a second. And again, the hope is that you can start to think about, are there things in my own systems that would be helpful to apply this to? Maybe, maybe not. We go back to this one, and this one again is an incident response system. So you can see there's a couple functions that don't have an input, and that's because they're the arbitrary boundary of where the system is drawn. Whenever you're studying a system like this, you've got to draw the line somewhere, and that's going to go back to what questions are you trying to ask? What are you trying to understand? Similarly, when it comes to these functions, and I'll circle back to this later, it's like at what granularity, what counts as a function, and what's like a sub-function? Depends on the questions you're trying to ask. Right? This is an iterative process. But in this case, we've got an example of a system. You've got alerts that are configured. Alerts can fire. They can be suppressed. A human checks them. They can escalate to their team. They can escalate to a partner team. Unrelated system changes can come in and touch a bunch of things. One of the notable things that stood out when I was building this one, and in some ways this is obvious, but in other ways it was validating to see exactly, is that authentication touches so many other things. If your authentication goes down, you're in big trouble, not just because it may cause an incident, but if it happens while something else is broken, you may be crippled in what you're able to do. That's why, we have backup measures in place. But that's an example. So how do we actually build the model then? Well, first is define the functions. Easier said than done, right? But you've identified your system, which you probably want to include people as well as the software. You've just established some rough bounds, and you're going to make multiple passes at this. Just pick a function to start with, and then you do that function. Then think about what's connected to it. Go downstream, go upstream, and then look at it and say, does this tell me what I need to do? If not, you can make a second pass. You can break and reorder the connections if they're different. You identify the functions, and then this is where you start to get that functional resonance aspect, and it's not just drawing some graph, but it's identify variability. So you look at your function and your functions and how they're all connected to each other, and you say, does this thing do the same thing every time? Or can it change? And if it gives a different output or a slower output, what happens to everything connected to it? Right? We talked about resources, for example. Right? If the disk space fills up, what happens to my system? And what do I have in place for mitigating that? Right. So if you look at types of variability, categories of variability, and yes, categories. Don't overthink the categories. Don't be a slave to the categories. But you can have internal variability, where something just takes longer to do, or sometimes it gives a weird output. Or you have external things. And the example of gas again, like how long it takes you to drive from point A to point B depends on whether or not you run out of gas and have to stop at the gas station along the way. right? External things. And then you can look upstream to look at the variability of things that can affect your system, and you can look downstream. The types are, output could be too early, output could be too late, output could never show up at all. It could be too weak, or too strong, or the wrong direction, or the wrong type, right? You might have the wrong type of variable come out of a software function. The wrong object. When it comes to sequencing, and right, this one tends to matter for people who worry about packets and for people who worry about database transactions, right? There could be an omission of something in the sequence of things you send. Something could be skipped, something could be repeated, something could be reversed. You could have extra output that you didn't expect. What happens to the things that receive that output as their input, or as its precondition, or any of these other things? These are the ways you sit and then chew on what you've then drawn to think about it. And part of how you do that is walk through incidents that have actually happened. Go back and look at an incident, preferably one that you've documented well. Easier said than done, right? But you can go and you can walk through your system, and it will teach you how the graph should have been drawn, and it will also tell you, well, this is actually pretty variable. Like, I thought this was a stable function that didn't change a whole lot, but the output was significantly different in this case, and that's part of the outage. Right? Because incidents are where the rubber meets the road. Incidents are revealing that how your system actually works as opposed to how you imagine it works. This exercise is an attempt to sit through and think through deliberately how your system works, so you can identify things that were fuzzy to you, things that you hadn't fully thought through, disagreements between coworkers about how things actually work. But incidents are empirical reality. They're an empirical proof of that things work the way you did or don't think. And then again, I talked about constructive and destructive interference. Do you have things in your system that dampen brittleness from above? Or do you have things that will make it worse? Right? There's examples of things like buffer bloat, where if the buffer gets really too big in a router, there's no mechanism for dealing with that sometimes, and that can cause a lot of problems downstream because you need things to arrive at a certain speed, and the router's being fast, but you've got to wait in your queue in the router for so long that it causes problems anyway. Even if, in theory, if the buffer was just deleted, everything would be working fine. So that's the general sense. You should have links to those diagrams, as well as how to make your own diagrams, as well as some homework for your first attempt at a diagram when you go to the handout. There's some software as well, including the software for building these diagrams. You can do them by hand, obviously. And the software we've linked to is okay. It's a little bit old, a little rough around the edges. I would love to do a rewrite. I just haven't had the time. I didn't write that software. It was built academically a while ago. There's also some research software called FRAM in there that will run through various instantiations. It can import a model from that other software, and then it can try a whole bunch of different instantiations. So you can you make your assumptions about variability, and then it will try a lot of combinations and show you where you're fragile. And anyway, it's really valuable stuff. I think it's cool, but in the end, like I said, it comes down to, is this helpful? How does your system actually work? All the time, we have drift between what we understood to be the system and what the system actually is. Not just because our memories are faulty, but because the system is always changing. Our coworkers are always doing things. Libraries update. Systems are so large that we can't hold the entire thing in our heads like it used to be the case decades ago. So anything you can do, whether it's incident analysis, whether it's modeling like this, any activity that forces you to reevaluate how the system actually works is valuable. At least that's my assertion. Thanks for taking a little bit of your time. Hopefully that's given you a new tool. If not, come talk to me and I'll see what I can do. This has been FRAM.